Hey everybody, welcome back to Calc 3 online. So today marks the start of a new unit in something called vector-valued functions, but actually what we're going to do is nothing related to vector-valued functions today. The plan is really to talk about what they call quadratic surfaces or hyperbolic surfaces, and the reason I do this now, it's actually in your book in the last section, but I find we don't really need it in that last section, but we're going to need it now, so I always think it makes sense to talk about something when we need it, and so we need it now, we got to talk about it now. So today is honestly one of those days where we really see the connection between just previous math classes and this idea I've talked about where Calc 3 is just adding z to something and notching it up a dimension, and all the stuff you're going to learn today really just builds off of Algebra 2, that, or pre-calc also, but everything to do with conic sections. So I want to start off and just review. There are 4 different conic sections. So you got your, in no particular order, your circle, right? Like your basic one, x squared plus y squared equals 1. But really, as long as these numbers below here are the same, like this could be pi, and this could also be pi, and that's a circle. You could have a parabola. That I don't think I need to say much about. You've been learning about these for years. Here you just have like y equals, x squared plus maybe something else in x. And then you can have a number if you want, like 7. But here you just have one of the variables squared, not both of them. And then you have, I don't know, how about ellipse? So an ellipse is kind of like a circle, but like say this one is pi. This just can't be pi. This could be the square root of pi. And as long as these two numbers down here are different, then it's going to basically stretch your circle in a certain direction. So in this case, because this number is bigger, it basically stretches it in the x more than the y. So you would get a ellipse that's sort of more in that direction. And I should probably also add that here and here, the center of the circle and ellipse was the origin because I'm not doing any shift in there. So how about for the hyperbola, which is our last conic section, let's do a shift. Let's do like x plus 1. We'll do over 4, and then we'll just do y minus 3, and then over, 16. And really to make something a hyperbola, it just needs to have one of the terms here be negative. It doesn't even have to be written this way. I mean, I can make that positive, and then that is still a hyperbola because now this one is negative. But this is so there's, with hyperbolas, right, there's sort of 2 cases. You can either have a hyperbola like that, or you can have a hyperbola like this. And the direction of it is determined by whichever one is basically positive. So this being the positive one means that we're basically going in the, we're going to have like a vertical or a Y kind of parabola where it opens up and down like this. And here, these numbers in here dictate the center, right? So the center of this thing would be -1, 3. It's always the opposite of those numbers inside. And that really actually boils back down to another Algebra 2 thing called like function transformations, but I'm not going to get into all this stuff right now. But I do assume that all of this is like prior knowledge for today. So I really hope that you understand the structure of circles, parabolas, ellipses, hyperbolas, because what I'm going to do today is basically take all these things and I'm just going to tack on something to them, and you'll see that when we look at surfaces, which is what the name we give 3D objects, right? These are, just graphs, 2D graphs, but as soon as I add a third variable to all these, they're really going to become surfaces. And if you understand these basic ones, then you'll understand what we're going to talk about today. So the first ones I want to talk about are what we call the quadratic surfaces. So this example, basically, if I blanked out this z term, right, it has the exact structure of an ellipse because you have a 1 under the x squared and a 9 under the y squared, so it's going to actually be an ellipse that moves more in the y direction than the x direction. And so as soon as I put the z term in, basically it just makes a 3D ellipse sort of thing. We actually call it an ellipsoid. A lot of 3D surfaces have this suffix oid added to it, but an ellipsoid basically looks like an egg. Sometimes people use egg to describe an ellipse, but it's not really correct because it's in the wrong dimension. But this one really is like an egg. So I can even actually draw it. So I could. It has its center at 0, 0, 0 because there's no numbers inside there. And so, its center is there. That's actually not part of the surface. But then in terms of x direction, if you take this and if you made the y and z term, so if you let y and z be 0, right? So you're basically on the x-axis. That's the idea. Then you're going to have x squared equals 1, so x is plus or minus 1. So for, extend this. So if you wanted to get oops, that is definitely not how we normally do that. Let me make that the -1. But basically, its direction in the x would be kind of going out to 1 and -1. And you could do the same thing for y, and you would see that it goes out to -3 or 3. And then in z, it goes to 2 or -2. And so it's not super easy for me to draw, but basically you get this sort of egg-looking thing that sort of is cut off in the front in the y direction by 3 and -3, and then over here at 1 in the x, and back here at -1, and then it sort of goes up to that 2 that I had there, and down to -2. But it's just an egg. And all of these things that we graphed today, actually, if you go to the math3d.org site, you can type in this, and it will literally graph it. You just need to use the implicit function setting in the drop-down menu, and you can see it a little better. But I just really want you to see some of these connections between an ellipse and an ellipsoid here. So really, if you deleted that term, you would have an ellipse, and now it's just a 3D ellipse. We call it an ellipsoid. So sometimes you get something that maybe you're struggling to see, and there's actually a technique called traces, which can help you kind of visualize it in a lower dimension. So it doesn't really come into play when you're graphing 2D things, because if you go one dimension down and look at what it's like in one dimension, it doesn't really help you. But if you're sort of thinking about projecting the 3D surface onto the different planes, so like the ZY here and the ZX planes, let's say. So let me just show you an example. So if I have x equals like 0, let's say, then the equation here would reduce to, I'm going to do this up here, we have 2z equals y squared over 32. And if you think about it, that is just a, it's a parabola, and it's going to open kind of like you're used to like x, y graphs. This one is just going to open like a normal parabola would, but on the zy plane, right? So that one is just going to be something like this, because it has, no shift in this parabola up or down. If I do something like, what's another nice one actually? Let's do x is 4. So if we do x is 4, the equation would become 2z equals 4 squared is 16 divided by 8 is 2 plus y squared over 32. And then if I divide by 2, I'm going to rearrange this a little bit too. I'm going to get y squared over 64 plus 1. And so if I graph that, if I put my 1 here, basically I'm just going to get some sort of parabola that's shifted up. And you could keep doing this if you want. You're just going to get, basically you're going to get parabolas that just keep going up like that. You'll just get different ones. So if you do the same thing and you look at traces for the other plane, like now, like let's let, y be 0. Okay, if you let y be 0, then you have 2z equals x squared over 8, or just z squared equals x squared over 16. And that also is some sort of parabola like that. If you try out, let's see, what's another nice one here? If you try out 8, then actually that's the one where we can get it up at 1. And if you just try it again here, you'll see also you just keep getting parabolas. You're going to get parabolas forever and ever and ever. And so then what you can kind of start to do is you can visualize sort of, okay, in this plane, when I look at the zy plane, when I project onto this plane back here, right, it looks like a parabola back there. When I project onto the zx plane, right, this plane right here, then it also looks like a parabola back there. And so we're basically getting, parabolas back in the zy plane, and we're getting parabolas in the xz plane. And really, if you try, it's not a perfect picture, but basically what this is going to be is some sort of bowl like this. I mean, it's infinite. It's going to shoot up forever and ever and ever. It's basically a bowl. It's like an ever-growing parabolic bowl. And the way we call this thing is a paraboloid. And it's basically whenever you have two variables squared, but one of them's not, you're going to get this, quadratic bowl-looking thing. And the fact that the z is the thing that's not squared means that it's going to shoot up in the, this is the z direction here. And like if I had, z squared and x squared but no y squared, then it's going to be a bowl that sort of is along the y-axis like this, okay? All right, so this is a different surface, and I just want you to think about using traces here to kind of get an idea of what this might look like. So here, when I say A, B, and C on the bottom, those are just like numbers. They're just some, real numbers that you're dividing by. And if you, let's start off with, how about, what's going to be a nice one? X equals A, okay? So if you do x equals A, and you try to think about what it looks like in 2D, you're going to get z squared over c squared equals 1 plus y squared over b squared. And if you rearrange that, you're going to get z squared over c squared minus y squared over b squared equals 1. And if you go back to like the very first slide here, that was just our basic structure of a hyperbola that is centered at 0, 0. And so when we do x equals A, we get a hyperbola that opens up in the z direction, like that. A weird one is if you let x equal 0. If you do that, you get z squared over c squared equals y squared over b squared. And really, like, we can boil it down to z squared equals y squared. We can just think of c and b being 1 for the time being. So if you've never thought about what this thing is, it's actually kind of a weird graph if you've never looked at it before. But basically, if you took like the square root of, like, say, both sides here, you actually have to introduce the absolute value. So you end up with a plus and minus because of the absolute value. So you would really get like z equals plus or minus y. So it's actually like this graph, if you plug it into like Desmos or something, you will actually get just 2 lines that are like right through the origin. So you get this line and you get this line right here. And if you do some more traces here, basically what's going to change is you would get, if x equals A, you'll get this nice one right here where it's 1. But basically if this becomes a different number, you're still always going to have the z squared minus y squared. So you're always getting a hyperbola that opens like up and down like this. So you can get like another one that looks like that. It would be like that. But you'll never actually be able to get something in these 2 regions. These green lines act sort of as like a barrier for the hyperbolas. So in this plane, the zx one, if you, I'm not going to go through all the math again because it's kind of the same math, but if you do y equals 0 in this one, then you'll get the weird like x graph. If you do y equals b, you will get the hyperbola right there. And again, you can get like other ones like this, but you'll never get one that's in here or in here, okay? And this one is probably worth doing. So let z equal to c, okay? If we actually, let's not do 2c. Let's do z equals just c. So if you do z equals c and you plug it in, you're going to get 1 equals x squared over a squared plus y squared over b squared, which is literally just a circle of radius 1. If you do, what's another weird one? If you do z equals 0, then you're going to get x squared over a squared plus y squared over b squared equals 0. And the only way this equation can hold, because everything in this is positive, the only way this works is basically if x and y are 0. So if you do the z equals 0 case, you're actually going to get the origin plotted. And if you do like bigger z's, so like if you did like z equals 2c, you're just going to get a bigger circle centered at the origin. It'll always be centered at the origin because there's no shift for x and y here. So if you start to try to think about what this looks like, basically when you look top down on it, it looks like circles. But then when you look at it from the side, you're going to get this weird hyperbola structure. And so like if you're looking at it kind of down this way, you see circles. And so if you think about it, basically what it has to look like, and I'm kind of running out of room, but I'll put it right here. What you get is really a cone. This thing is a cone. And that's a pretty bad cone right there. So you would get this sort of cone structure. And it has sort of these asymptotes almost that come from the y equals 0 or x equals 0 traces. And but then when you look at it top down, you see that circle structure. So this is actually a circular cone. And yeah, that one I always thought was kind of weird. And personally, sometimes I still can't like remember what all these are just by looking at them right off the bat. So I just go through this kind of stuff quick, and I can start to kind of visualize it. I can be like, oh, okay, that's, circles here, hyperbolas here, so it has to have some sort of cone structure. All right, so I just want to do an example where it's not super obvious what it is yet, and I want to just kind of simplify this and show you that it really is this graph right here. It's probably not super hard to see because there's only two things that are squared, but basically the issue could be, is it going to be an ellipsoid? Or, sorry, not an ellipsoid. Is it going to be a paraboloid in a certain direction or not? So it can be hard to tell, just given like a random standard form kind of like this, which way the paraboloid points. So let's turn it into a form that we're kind of a little more comfortable with, where we can see like the shifts and things like that. So the way we do this is basically just complete the square. So I'm going to combine the x's. I'm going to leave a little spot to complete the square there with the x's. And then you don't need to complete the square with the z's because there's only one z squared term. And then I think I'm going to move the y to the other side. And I always like to just move the number to the other side because I'm going to put something in here, so I need to add it to that. Okay, so if you complete the square, right, working with the -6, this would be a 9 because it's just -3 squared. So then you need a 9 over here to balance it and make sure that you still have the same equation. This part would combine, or would factor into x minus 3 and x minus 3. And then we just got the rest of this plus 2z squared equals y minus 1. And so I'm probably just going to move that minus 1 back over now, just because I'm kind of used to writing paraboloids as like one variable equals something else. And so you can actually figure out like this vertex from here, right? If you look at the numbers like inside the squared terms and then this number on the like the shift in the y, you can get the vertex. So the vertex just needs to be you're shifting it 3 to the right in the x, so positive 3. You're not shifting it in z, so we can even put the 0 there. And then this plus 1 is really the y shift. It's like you're moving up 1 unit in y. So the vertex should be at 3, 1, 0. And, the range of this graph, it just asks for the range, would be then You starting at 1 and you just go out to infinity. It's like that idea that this is like just a parabola that opens forever and ever and ever and ever in the y direction. So, I think this form is much easier to read than looking at that. This thing is a bit unclear as to what's going on. All right, so this question is kind of just uses traces, I guess, again, is how I would think about it. You might be able to just see what this would be, but the question is, if you take x, y, z, and you have down here in x, y, z, the square root function. I'm going to do a different color. So square root function is like going to be like that, right? And the idea is like if you take that and you rotated it around the x-axis, so one of them, like you get, would be kind of the mirror image over the x-axis. But you're going to end up getting, right, this sort of parabola bowl structure again. Again, it's infinite. Like there's going to be one there, one there, one there. It's not a perfect picture, but it kind of works. So this is a paraboloid, again. Paraboloid. But the question is, what's the equation of that surface? So the way I would think about it, I know it's shooting like down the x-axis, so it's going to be x equals, and then the y and the z terms are going to be the squared ones. And the way I would kind of just figure out how much, I guess, is sort of thinking about 2D again. So like if you take, x, y, and we think this is square root of x, right? Then we know this is negative square root of x. If you think of the equation of that graph that I just drew here, let's make it a different color, this yellow one. This yellow graph is actually just x equals y squared, right? There's been no stretching or compressing of the the y squared term, and so we don't need to stretch or compress our original one here. So the equation would actually just become straightforward y squared and then plus z squared, and that really would do it. It can get hard to know, if there had been some sort of stretching or compressing, what numbers to kind of put here in it, like the way I had some numbers here. And that part is, really, if you needed to figure out these scaling numbers, you'd probably just use a computer and, model it. It's kind of beyond the scope of what I want you to be able to do. I mostly want you to see that, the similarities between a parabola and a paraboloid here, and see that we can start with a 2D graph like this, and if we do these rotations, it's not too hard to see that we would basically have this surface. And then if you go to Math 3D and you plug this in, you will see that that is actually exactly what that surface looks like.